Good morning, everyone. So we're going to be looking at our lesson 3. This is going to be all about calorimetry, and this is one of the lab that we're going to be doing. So when we look at calorimetry is an experiment to determine the amount, I'm just going to put the number of joules of energy released by an object. Okay, and so sometimes this object might be, like in the picture, it might be this metal block, right? Because we can use its specific heat to identify it, or it might be a particular food. We're actually going to be doing this version of the experiment in class. For the most part. Now, when we do this calorimetry experiment, there are two basic assumptions that we make. One is that all the heat released by the object is absorbed by the water. Absorbed by the water. So for example, when we're burning this Cheeto, we assume that all of this heat goes only into the water and not into the air or the can or things like that. Even though we know it does, we make the assumption that it's not going to because it will make the math really complicated. Let's just put it that way. Same thing with the metal. We assume that all of the metal, all the heat released by the metal gets absorbed by the water, which makes sense because it's in the water. The second assumption that we make with calorimetry experiments is that the final temperature of the water is equal to the final temperature of the object. Okay, that these are the same things. So our two basic assumptions in more of a symbolic terms is that if the heat that is released, so it's exothermic, it's negative, by my object is equal to the amount of heat that is absorbed by the water. And the other thing is that the final temperature of the object is equal to the final temperature of the water. These are the same things that we're looking at. Now, when we do a calorimetry experiment, you're going to have a couple of basic setups. Your first thing that you're going to do with this one, so this is kind of what it looks like if you're setting up the calorimetry of an unknown metal. What you do is you heat the metal to a very particular temperature. You heat it up, and then you add the metal to the water. Okay, and when you do this, like, you already know the mass of the water, you know the metal, and when you add the hot metal into the water, the thermometer is going to rise. And then whatever that final temperature is, it will be what you have. Now, for our food experiment, what you do is you take your food item, this kind of looks like a bean or a Cheeto or something, on there, and you stick it on a cork with a pen, and you light it on fire, and the fire goes into the aluminum can, and there's a certain amount of water in here that we already know, and you have a thermometer in here as well, and you measure the temperature. Okay, so let's look at the math examples of this. So in example 1, it says pellets of an unknown material were heated to 95 degrees Celsius and then transferred to a calorimeter containing 175 grams of water at 20 degrees Celsius. The highest temperature recorded was 23.6 degrees Celsius, and 96 grams of the metal was used. Calculate the specific heat capacity of the unknown metal. Okay, so here we're going to use this to help us figure out the specific heat capacity, which is C, of our metal. That's what we need to figure out. And one thing we can do to help us stay organized is to split things up between our metal and the water. So let's think about what we know about the metal. We know that the metal was initially at 95 degrees Celsius. Okay. And we know that so that was this number. It says it was transferred to a calorimeter containing 175 grams of water. So the mass of the water is 175 grams. And it is initially at 20 degrees Celsius. That's our third value. It says the highest temperature recorded was 23.6 degrees. Now this is special because remember our second assumption was that the final temperature of both the water and the object are the same. So if we know that our final temperature of the water is 23.6 degrees, so it heated up, we also know that the final temperature of my object, my metal, is also 23.6 degrees, so it cooled down quite a bit. And it says 96 grams of the metal was used, so grams is mass, so we know that mass is 96.0 grams. Now, one piece of information that we do need is we need to know the specific heat of water, because we need that to calculate this. It is on the back of your periodic table. It's also in our last lesson's notes. But the specific heat of water is 4.184 joules per grams degrees Celsius. And so when you do this kind of problem, the first thing you do, step number 1, is you calculate Q for water. So you do everything for water first, okay? So we know that Q is equal to mc delta T. So we know that the mass of our water is 175 grams. We know that our specific heat of water is 4.184 joules per grams degrees Celsius, and that the final the change in temperature is 23.6 degrees Celsius minus 20 degrees Celsius. So if we simplify this, we know that Q of our water is going to be, we know that 23.6 degrees minus 20 is just going to be 3.6 degrees Celsius, so I can simplify that. So 175 times 4.184 times 3.6 is a positive 2,635.92, and my unit, degrees Celsius cancels out with degrees Celsius, grams with grams, so all I have left is joules. Now, this is important that we note that this is positive, because that means it was endothermic and it was absorbed, right? And so we know that why did the water heat up? The water heated up because we put this really hot metal inside of it. And so what we know is that if our Q of the water is equal to positive 2,635, what that tells us is that Q of our metal has to be the opposite. It's negative 2,635.92 joules, okay? And so our second step number 2, is going to be to calculate the specific heat of our metal. So we're going to look for the C of our metal. Well, again, remember, Q is equal to mc delta T. But now we're doing everything for our metal. So we already used all of these values, and we're not going to use them again. So we know that Q of our metal is negative 2,635.92 joules. I'm going to put it in parentheses just to make sure I keep my negative sign with it. And it's times my mass, so 96.0 grams, times the specific heat of my metal, which I do not know, so I'm going to leave it as its variable, times my change in temperature, which is 23.6 degrees Celsius, minus 95 degrees Celsius. Notice that this is going to give us a negative number, but that's good because we know that it cooled down, the temperature decreased. So 23.6 minus 95.0 is going to give us a negative 71.4 degrees Celsius when we simplify. And so we can also simplify the right side of the equation. So if we keep the left side the way it is, then we can multiply 96 times the negative 71.4, and when we do that, we get negative 6,854.4, and those units are grams degrees Celsius because we have both of them there, none of them canceled out, and it's still multiplied by the specific heat of our metal. And to get the specific heat of our metal alone, we will need to move it to the other side. So we'll divide by negative 6,854.4 grams degrees Celsius on both sides. This cancels out, and that tells us that the specific heat of our metal is going to be equal to, well, one thing we notice is that our units, none of them cancel out, which is good. So we have joules per grams degrees Celsius, which is what it's supposed to be. A negative divided by a negative is positive. So 2,635.92 divided by 6,854.4 gives us 0.385 joules per grams degrees Celsius. And what's great about this is that, remember, this value is unique to each element. So if we know the specific heat, we could determine the identity of this unknown metal if we had a list of metals and their specific heats in their chart. Let's take a look at example number 2. So this is just another way of looking at it, but in a slightly different way. Our data is already given to us in a chart, which is nice because it's already organized. So we know the mass of the empty cup. So this is going to be similar to what we do in our lab, well, a different lab. The mass of the empty cup, the mass of the cup plus water. So we know that if this is the mass of the cup plus water, and this is the mass of just the cup, that I can subtract those two to find out just the mass of my water. So what I can say, okay, is if I take, let's just do that down here. The mass of my water would be equal to 180.89 grams minus 2.31 grams. So 180.89 minus 2.31 gives us 178.58 grams. We also have the mass of the cup plus the water plus the metal. So if I want to know just the mass of my metal, I can subtract the 780.89 minus the 180.89, and that should tell me the mass of my metal. So that's 600 grams. Now they tell us the initial temperature of the water, so the initial temperature of my water. They tell me the initial temperature of my metal, and then the final temperature of the water, which we need to remember is also for the metal, is 27 degrees Celsius. So if they want to know the specific heat capacity of our unknown metal, remember step number 1 is we need to find Q for water, the heat of water. So Q equals M, so we're just going to put this up here. Q equals MC delta T. So the mass of our water was 178.58 grams. We know the specific heat of water is 4.184 joules per grams degrees Celsius. Remember, that is on the back of your periodic table. And the change in temperature we know that the final temperature of the water was 27.0 degrees Celsius minus the initial temperature, which was 17.0 degrees Celsius. So as we begin to simplify, we know that this is going to be 10 degrees Celsius times our original values. And so we find out that Q of our water, 178.58 times 4.184 times 10, means that it has absorbed, so it's positive 7,471.79 joules. Okay, so we have this many joules of energy that has been absorbed. And so this tells us that Q of the metal must be the opposite. It must be a negative 7,471.79 joules, because if the water absorbed heat, it had to come from somewhere, and it in fact came from our metal. So now we can use our Q equals MCAP formula, but for the metal, to solve for the specific heat. So we know that negative 7,471.79 joules will be on our left side. That's Q equals MC delta T. So our mass is 600 grams. We do not know the specific heat of our metal, and our change in temperature is 27.0 degrees Celsius minus 52 degrees Celsius. So that's going to give us a negative temperature because it cooled down. And when we divide this, we see that we would get negative 25 degrees. And if we multiply that by 600, then we know that our right side of our equation is negative 15,000 grams degrees Celsius times the specific heat of metal, which is equal to negative 7,477.79 joules. We subtract, or excuse me, not subtract, we do the opposite of the math. So we divide by negative 15,000 grams per degree Celsius in order to get the specific heat of our metal by itself. And so this cancels out, and that means that the specific heat of our metal, we've got units of joules per grams degrees Celsius. Negative divided by negative turns positive, so 7,477.79 divided by 15,000 gives us a specific heat of 0.499 joules per grams degrees Celsius. So this is how you do your math. This is kind of what the experimentation looks like. You have some practice problems underneath, and this is also kind of the same calculation you'll be doing in your lab experiment. So if you have any other questions, there are other calorimetry videos on my YouTube channel that you can take a look at. You can also come to tutoring and ask.